All right, so let's get started here. So first things first, let's just note our next exam, our last regular exam, exam 4 will be on Monday and Tuesday of that very last week of classes. So normally it's Tuesday, Wednesday. This particular exam is going to be on Monday and Tuesday, so please make a plan to be able to take exam 4 in the testing center on either Monday the 6th or Tuesday the 7th. All right, we're going to pick up where we left off last time. We talked about how if we can combine two reactions to make this overall reaction here, then we can also combine the enthalpies of those reactions to figure out what our overall reaction's enthalpy is. All right, we worked on summing up these chemical equations last class. I never name dropped the dude, but this is what's called Hess's law. All right, Hess's law states that the change in enthalpy of a reaction is equal to the sum of the enthalpy changes in stepwise reactions that sum to your overall. All right, so these individual reactions here that we summed up, we would call these our steps. So this one was step 1. This one was step 2, so we have these individual steps, and they sum up to give us this overall reaction. Likewise, we can take the enthalpy of each of those steps and sum them up to get the enthalpy change of our overall reaction. All right, so if we can sum our chemical equations to make this new one here, which we're going to call our overall reaction, then we can sum up those steps, the enthalpy change of those steps, to get the enthalpy change of our overall reaction. All right, and this is kind of a pain in the butt way of calculating our enthalpy change here, but something that's really important and something that we can take advantage of. Sometimes it's really hard to measure a particular reaction, and it's easier to break it up into these steps that are easier to measure. And then we can get the enthalpy change of the overall by summing up those steps. All right, so that's calculating our enthalpy using Hess's law. Let's do the easy way now. All right, now we're going to learn how to calculate enthalpy using that constants page of thermodynamic standards. All right, these correspond to those formation reactions, and why we get to use that constants page is the exact same logic as Hess's law. Each of those values on our constants page correspond to one of those formation reactions, and we can sum up those formation reactions in a way to create our overall reaction, right? But the process is a little bit more straightforward. We're going to look on our table here, and we're going to take the sum of the delta H of the products multiplied by their stoichiometric coefficient. And we're going to subtract the sum of the delta H of the reactants multiplied by their stoichiometric coefficients. And that will give us the delta H of our reaction. All right, so what you kind of want to remember, what you want to be chanting to yourself so you don't mess this up, is products minus reactants. That's what we're going to do. We're going to look up the value for our products, look up the values for our reactants, take the products minus the reactants. All right, so let's take a look at a sample reaction here. We're going to do HCl gas plus CH4 gas. That will give us H2 and CH3Cl, all gaseous here. All right, and when we look up our compounds, it's really important that we look for exact matches. All right, not just the formula, but also that state of matter as well. We need an exact match for each one of these in our chemical equation. And as long as we can find those compounds on our constants page, we could do this game for any chemical reaction. That's the nice thing about these thermodynamic standards. All right, so let's take a look here. These are our 4 compounds that we're trying to look up. So we're going to go to our constants page of all of these thermodynamic standards here. All right, so first we're going to look under hydrogen. Everybody find the relevant value that we need under hydrogen. I guess just to be clear, our first column is the only one that we care about in this course, the delta H's of these reactions. We don't know what delta G and S are. That's saved for a future course for your Chem1B course. The only thing that we're talking about is these delta H values. All right, but we're going to look up each of these compounds. So take a second. What value do we need for hydrogen here? We're trying to look up each of these compounds in our chemical equation. One of them is that H2 gas. So I'm going to record that delta H value of 0 for hydrogen. All right, we got to continue to find our values here. Oh, they're all going to be up, alphabetical order. All right, so now look under carbon. There should be 2 compounds from our balanced chemical equation that you can find on this list here. We'll zoom in as much as possible, but everybody take a second and grab those values that we need to look up. All right, we got 2 of our compounds from our balanced chemical equation on this page right here. All right, so the first one is that CH4 gas, so we're going to record that negative 74.6. And then we see our product, the CH3Cl gas. We're going to record that negative 89.1. All right, so now we have one more to go, and that one was HCl, or for with chlorine. So carbon, chlorine. All right, and I got 2 HCl's here. Which one am I going to grab? The gaseous one. Again, you got to match the state of matter as well as the formula. That's very important. So we're going to do HCl gas, which is negative 92.3. All right, so let me just summarize here what we just found. Here's our balanced chemical equation. I guess I should have told you to balance it, but it is balanced as is. All right. And now we're going to do our delta H values for each of these compounds here. For HCl, it was the negative 92.3. The methane, CH4, 74.6. Hydrogen was 0. And then CH3Cl was 89.1. And these are all kilojoules per mole. Those are our units for delta H. All right, so then everybody take a second and calculate the delta H of this reaction by taking the sum of the products and subtracting the sum of the reactants. right, so I'm going to take the sum of the delta H of my products, and I'm going to subtract the sum of the delta H of my reactants. Importantly, you need to put this reactant side over here in parentheses so that this minus sign is correctly distributed. If you did not put those parentheses in there, you would hit this negative 92.3, but the minus sign would not touch the negative 74.6, and you get the wrong number. All right, so make sure you I put both of them in parentheses, truthfully, order of operations wise. The reactants is essential to put in parentheses, or you will mess up your order of operations. All right, and if we punched it into our calculator correctly, we would find that the delta H of this reaction is 77.8, and again, those units are kilojoules per mole. So given this value here, what can we say about this reaction? Is it endothermic or exothermic? Endothermic. This positive delta H corresponds to an endothermic reaction. Okay, so given our balanced chemical equation, we're going to go to our constants page and we're going to look up all of those delta H values from our thermodynamic standards. And then we're going to take the sum of the products and subtract the sum of the reactants to get the delta H of our overall reaction. All right? Okay, we're going to play this game a few more times here, but now we're going to talk about a specific type of problem, specific type of reaction. And these we've studied before. These are our precipitation reactions. Precipitation. I don't know if that's correct spelling. It doesn't look right. Anyways, moving on. Precipitation reactions. That was where we take these two aqueous solutions and we mix it together in order to get this solid product. So for example, if we took a solution of iron 2 chloride and mixed it together with a solution of potassium carbonate, we would see this solid precipitate form, this iron carbonate, iron 2 carbonate, which would be a solid. It would precipitate out of that solution. And then we would have the potassium and the chlorine still floating around, right? Still aqueous. And we discussed this type of reaction at length. This was one where we could actually predict the products of this reaction. Given just our reactants here, we could say that solid iron 2 carbonate is going to form based on that solubility chart that we had, right? So when we were learning about chemical reactions, this was one that we learned how to predict the products of. So now let's go ahead and calculate the enthalpy of this reaction here. Does this reaction absorb or release heat when this precipitation is occurring? All right, and let's focus first on this one compound here, our iron chloride aqueous. If we go to our constants page, and we go to iron, again listed alphabetically. Oh look, it's right there. Cool. We're going to look up our reactant here, our iron 2 chloride. Awesome. But what's the problem here? It's a solid. This is not the correct state of matter. And in fact, if you look, you're not going to find aqueous iron 2 chloride anywhere on this chart here. All right, so how do we deal with these precipitation reactions? Well, remember when we did our precipitation reactions, one of the things that we learned how to do was to create our net ionic equation. And when we created our net ionic equation, it was all about canceling things that were aqueous on both sides. So my chloride's aqueous on both sides, and my potassiums are aqueous on both sides. Those are what we called spectator ions. And the name spectator ion was because they're not actually participating in the chemical reaction at all. They're just floating around watching it go down. So these spectator ions aren't going to have any influence on the release or absorption of heat of this chemical reaction. They're not participating in this chemical reaction. So for precipitation reactions, when we go to calculate the delta H, we need to do the delta H of that net ionic reaction. So I'm not going to be able to look up the iron 2 chloride aqueous or the potassium carbonate aqueous. Instead, I'm going to write my net ionic equation for this reaction, which would just be those aqueous iron 2 ions and that aqueous carbonate ion combining together to form solid iron 2 carbonate. And these we'll be able to look up on our constants page and play that same game that we did with our previous products minus reactants. All right, so again, this is what we called our net ionic equation. I would just say that if you are having trouble with this assignment and doing your net ionic equations, please remember we did this earlier in the course, and you can always go back to that assignment and practice doing those net ionic equations again. All right, so now we need to look up all of our reactants and our products from our constants page. So we're going to go back. Again, I couldn't find that aqueous iron 2 chloride, but I can find my aqueous iron ions. All right, there's going to be one other important compound that you'll be able to find on this chart here. So everybody take a second. Another one of our products or reactants is listed right here. And that would be this iron 2 carbonate business here. All right, to look up my carbonate ion, I'm going to have to go to a different portion of my chart. I'm going to have to go to my carbons. So we'll go back up. All right, and I want not aqueous carbon dioxide, but aqueous carbonate with that net charge of -2. So I'm going to list that -677.1 value as well. All right, so now we have all of our things found on our page here. So just to summarize, our delta H that we looked up, again in kilojoules per mole, for that iron ion was -87.9. The carbonate was -677.1. And then the solid precipitate was -740.6. So everybody take a minute and tell me the delta H of this reaction here, of this precipitation reaction. So I took in this case I only have my one product, so I took my product's delta H and I subtracted the sum of my reactants. And again, I was really careful about distributing that minus sign, so I put my sum of my reactants in parentheses before punching it into my calculator. All right, and then punch that into my calculator. I get a value of 24.4, and again, that's in units of kilojoules per mole. So that's my delta H for my precipitation reaction. This reaction is also endothermic. All right, that positive delta H value. All right, so for our precipitation reactions, we will not find all of these aqueous compounds on that chart. Instead, we're going to look at the net ionic equation, because those spectator ions, in this case the potassium and the chloride ions, they're not actually participating in this chemical reaction at all. They're not involved in the formation of this new bond in my solid here. So all I need to do is look at my ions that are involved in my reaction, my net ionic reaction, and look those up on our constants page along with that solid product, and that's how I can determine the delta H of these precipitation reactions. All right, so let's just practice one more here. It's been a minute since we've done these net ionic equations. All right, we're going to do silver nitrate. Plus sodium sulfate. This will give solid silver nitrate and aqueous sodium nitrate. All right, we got to balance this chemical equation. Let's be careful. All right, previously it was 1 to 1 to 1, but we got these coefficients of 2 out front of the silver nitrate and our sodium sulfate. So now everybody take a second and give me the net ionic equation. All right, so I got my net ionic equation. I have these 2 outside of my coefficient for my silver nitrate, so I better have 2 silver ions, my sulfate ion, and then my product, which I'm missing my subscript of 2 down here, my silver nitrate, right? So the things that are aqueous on both sides, the sodiums and the nitrates, will cancel out here. For the sake of time, I went and looked up those values for the delta H of each of our products and our reactant, or each of our reactants and our products. So everybody take a second and give me the delta H of this overall reaction here. right? Again, I'm going to do my product, that negative 715.9, minus my reactants. I'm going to put my reactants in parentheses. My delta H of that silver ion was that 105.8. So when I'm doing my calculation here, I have 2 times that 105.8. Why did I multiply that 105.8 times 2? Because of my coefficient of 2 in my balanced chemical equation, right? It's got to be the sum of your reactants multiplied by their stoichiometric coefficients. If we look at our formula here, we got this N in our formula. Those are our stoichiometric coefficients. All right, so if I have 2 silver ions, it's going to release twice as much heat as 1 silver ion, or I guess absorb, it's positive. Okay, so I punch that into my calculator and I get a delta H of negative 18.2 kilojoules per mole. So what can I say about this precipitation reaction? Is it endothermic or exothermic? So this one would be exothermic. My delta H value is negative. All right, cool. So that is a super powerful method of being able to calculate these reaction enthalpies using that constants page. As long as I can find all of my reactants and all of my products on those thermodynamic standards page, I can figure out the delta H of that reaction. All right, big caveat, it's got to be an exact match here. All right, so for our precipitation reactions, you're going to first find the net ionic equation. And those are the compounds that you look up on that constants page. All right, we're going to have one more method of doing this here, calculating our delta H. And that is using what's called bond dissociation energy. So now we're going to learn how to calculate delta H using bond dissociation All right, so let's take a look at a chemical reaction here. And we're going to draw out the Lewis structure of these compounds as well. All right, the very first reaction that we did in class today was HCl plus CH4 gives us H2 and then CH3Cl. And now we're going to look at this same reaction, but we're going to look at our Lewis structure here. Right? Our Lewis structure shows us who's bonded to who. Okay, so the same reaction, just drawn out with our Lewis structures here. Okay, and remember, chemical reactions are all about making and breaking chemical bonds. So if I look at my Lewis structures here, I can look and see which bonds are being broken and which bonds are being formed in this chemical reaction. All right, so I want you to look and play the spot the difference game. What's different from both sides here? Which bonds are being broken and which bonds are being formed in this reaction here? right, I'm going to color my bonds broken in red and my bonds formed in blue here. All right, and I'm just going to look carefully and play the spot the difference game here. On my left-hand side, I have H bound to chlorine. On my product side, it's carbon bound to chlorine. So this reaction, we got to break this bond here. And we're going to create or form this new bond over here. What other bond am I going to have to break on my reactant side? This carbon has how many hydrogens? 4. This carbon has how many hydrogens? 3. So I got to get rid of one of them. I got to break one of these carbon-hydrogen bonds as well. And then on my product side, one of my other new bonds will be this new bond between these two hydrogen atoms. All right, so in red here are my bonds broken. We got to break our bonds of our reactants. And then when we form our products, we're going to create new bonds here. All right, in order to break bonds, you have to put in some energy. All right, so breaking bonds requires an input of energy. But when those new bonds form, those new favorable interactions form, that process will actually release energy back out. So a chemical reaction is about making and breaking bonds. You got to put energy in to break the bonds. But those new bonds that are formed will release energy. All right, so this, when new bonds will form, that will release energy. So then what is bond dissociation energy? This is the amount of energy required to break a bond. All right, so we have this chart here. This is our bond dissociation energy chart. If I look up a particular bond here, so for example, an H and Cl bond, I get this number, 431 kilojoules per mole. That's how much energy you have to put in to break a hydrogen-chlorine bond. Right? So what this table is telling me is that 431 kilojoules per mole is required to break a HCl bond. All right, you see we get kind of lazy. We should have our lone pairs in here for it to be a proper Lewis structure. We get kind of lazy. Truthfully, as you go on, you get really good and you just know those lone pairs are there when you get to higher levels of chemistry. Nonetheless, so anyways, you see them omitted on our table here. It's the same thing. All right, so that's what that's telling me, is that I would require 430 kilojoules per mole to break that bond. That also tells me that 431 kilojoules per mole is released when a HCl bond is formed. right, so we can use this chart here to predict our enthalpy of our reaction. All right, we're going to calculate how much energy we have to put in to break all these bonds on our reactant side. But then we're going to also calculate how much energy is going to be released when all those new bonds on our product side form. And the difference will be the enthalpy of our reaction. All right, so let me just copy down again just to have it right here, our chemical reaction that we were looking at for this example. We said HCl plus that CH4 gives us H2 and we said that we got to break these bonds and we're going to create these new bonds in this reaction. All right, so let's figure out here how much energy is required to break these two bonds. We're going to look them up on our table here. I have an HCl bond that I'm trying to break here, so I'm going to look right here. That's going to require 431 kilojoules per mole. And then I'm going to add the other bond I have to break, which is a carbon-hydrogen bond. So I'm going to look on my table here, find that correct bond. That'd be this one here. That requires 413 kilojoules per mole. All right, so this tells me that I'm going to have to input a total of 844 kilojoules per mole. That's what I need to input to break my bonds. All right, I guess we can keep our language the same here as we did previously. That's how much energy will have to be absorbed by these two compounds to break those bonds. All right, so now I want you to play the same game that we just did, but I want you to tell me how much energy is going to be released when we form our new bonds. All right, so I find that this 764 kilojoules per mole is released when these new bonds form. All right, so first of all, this reaction will absorb 844 kilojoules per mole, but then release 764. So the net result here is that I need to absorb more energy than I'm going to release, right? So this reaction right here would be endothermic based on these values. So how do we calculate our delta H based on these values? Our delta H of our reaction is going to equal the sum of the bond dissociation energy of the bonds broken minus the sum of the bond dissociation energy of those new bonds that are formed, right? Absorbed means that we have a positive amount of delta H, a positive enthalpy, whereas released means a negative enthalpy. So it's going to be bonds broken minus bonds formed here. And so we see we end up with an overall positive delta H of our reaction, whatever that difference is, 844 minus 764. Total of 80 kilojoules per mole. All right, and if we compare that back to what we got at the very beginning of class, we did this exact same reaction, but we looked it up on that constants page. And we got a very slightly different value of 77.8, very close to 80 here. All right, this bond dissociation method here is a good approximation, but it's not perfect. All right, so then why would we use it? Because we can use this to look at compounds that aren't on that constants page. There's a lot of different compounds listed on there, but there's a whole lot more different molecules out there. And there's a ton that aren't on that thermodynamics standards page. So how would we deal with those? Well, we got to approximate them by paying attention to what bonds are broken and what bonds are being formed, and we can estimate the change in enthalpy of that reaction using these bond dissociation energies. All right, so it's not perfect, but if we don't have those values on our constants page, this is the next best thing right here. All right, so for example, let's take a look at another one here. I'm going to give you another problem that wouldn't have been on our constants page that we couldn't look up using our thermodynamic standards. All right, so the name of the game is going to be the same. We got to first figure out what bonds on our reactant side are being broken and what new bonds on our product side have been formed. Once we do that, we're going to sum up the energy required to break those bonds and the energy that's going to be released when those new bonds are formed. And the difference will be the overall change in enthalpy of our reaction. All right, so everybody take a second and see if you can't finish this problem here, identifying what bonds are being broken and what bonds are being formed, and then calculating the delta H of our reaction here. All right, so I look it up for my bonds that are being broken. My carbon-fluorine bond will require 485 kilojoules per mole. My nitrogen-hydrogen bond will require 391, so I'm going to have to put in 876. But when my new HF and CN bonds are formed, it's going to release 860. So my broken minus formed give me a net positive number here of 16 kilojoules per mole is going to be absorbed in this reaction. All right, so we can predict the enthalpy change of our reaction by looking at how much energy we have to put in to break these bonds and subtracting how much energy is going to be released when these new bonds are formed. All right, so this is our third and final, don't worry, we don't have another one to tack on here, method of calculating our enthalpy for a reaction. All right, looking at bonds broken and bonds formed and using these bond dissociation energies. Cool. All right, enjoy your weekend.